All right. So, good evening, all once again.
Good evening.
Hope we
Good
had a
evening.
great day and a great break.
Well,
And I and I believe the exams we have done justice with, and I've given the instructor marking scheme. All right. So, we're going to continue today. From where we stopped last class. So, if you permit me, I will share my screen. I'm about to share my screen now. I'm on it. So, if you can see my screen, you can let me know. Can you all see my screen?
yes.
Yes.
All right. So, this is our topic for the day: estimation and series by varied, discrete, and continuous distribution. It's PMF and PDF. By PMF, we mean probability mass function, and by PDF, we mean probability density function. And if we remember, in our previous classes, we see that PMF is for the discrete random variable, while the PDF describes the probability distribution of the continuous random variable. So today we are going to talk about estimation and series, and then particularly we are going to look at the bivariate discrete and continuous probability distribution, its PMF and PDF. So I remember my humble self, Anzaku Jacob. I'll be taking the class together with Ilyasu 80. All right, so our table of contents for today will be what we have on the screen. So basically, we're going to have a brief recap. We'll look at an introduction. We'll look at bivariate or joint distributions for discrete random variables. By the way, anywhere we see bivariate, we're trying to talk about the joint distribution. Recall in our earlier classes, we mentioned something like univariate, bivariate, and multivariate. We say that univariate means we are dealing with one variable, bivariate we are dealing with two from bi, bicycle and so on. And then when we say multivariate, we say when there are more than two, three or more, then we are dealing with multivariate variables. So when we say bivariate, we are actually talking about joint, because actually what we are looking at is how we can join the two variables together and find their probabilities. So that is basically what we'll be doing. So when we see bivariate, let our mind just go to joint. And when we see joint too, let us quickly think of it as bivariate. So we're also going to have the definition of the joint discrete probability function. We will also look at the marginal distribution for discrete random variable. Marginal, what does it mean to be marginal? When we say we're looking at the marginal distribution of probabilities, what are we doing? We're going to understand all this is how to use the marginal distributions in estimating problems, especially as it concerns actuarial science. And then we'll look at the joint distributions for discrete random variables. We'll look at the marginal distribution for uh, continuous. Okay, sorry, this should be joint distribution for continuous random variables, and then the marginal distribution for continuous random variables. Then we'll look at conclusion. In all this, we'll also be seeing one or two examples that will help buttress the point we're trying to make as it regards today's topic. All right, so a brief recap. We recall in our previous classes, we talk about a random variable, and we say a variable uh, is a quantity that can take any value. The value varies, and that's why it can assume any value, and that's why we say it's variable. And we say because it is random, we say it is a random variable. And we say it is random because in an experiment, we don't actually know the true value. So it is when we conduct that experiment or the event occurs that we can know that this is actually the value, and that is why we say it is random variable. It occurs at random. We also talked about probability. We define probability, the conditional probability, and also we define the frequency approach to probability. We talk about probability distribution. We see probability distribution is a measure of the behavior of a random variable. So how the random variable behaves is we can use the probability distribution to measure it. We also talk about the moment generating function, remember? And we say the moment generating function is useful because it helps us to derive some qualities or some properties of a particular distribution. It can be the skewness or the kurtosis and so on and so forth. We also talked about the discrete probability distributions. We say when we say discrete, we are looking at basically in practice, we are looking at a discrete value like an integer, 1, 2, 3, and so on and so forth. And then we look at the CDF, the PDF, and applications in actuarial mathematics. And some notable discrete probability distributions were the Bernoulli probability distribution, the binomial, uh, the uniform, the discrete uniform distribution, the geometric distribution, the Poisson distribution, and so on and so forth. You can go on and on and on and on. And I think this is one of the questions that came out in the exams, right? So we also looked at the continuous probability distributions. We look at some examples and applications in natural mathematics. We see that the continuous probability distribution measures the probability of values in a continuous case. And we say we think of it like a value with decimal places because it's continuous. And then we also look at some examples, which includes the normal distribution, the continuous uniform distribution, the beta distribution, gamma distribution, exponential distribution, and so on and so forth. We see that there are numerous distributions. In fact, there are some distributions that are joint. Like you can hear of the gamma Weibull distribution. You can hear of the inverse exponential distribution. You can hear of the beta Weibull, and so on and so forth. So there are plenty distributions, but basically we use these common ones that we mentioned, and we explain some of their applications in actuarial mathematics, giving some examples, and we looked at all those things. And I believe that by now uh, we can look at any event or any distribution, and we'll be able to assume that it follows a particular distribution, right? I believe that will be a piece of cake, right, Mrs. Abun?
Yes, yes, yes.
All right. Thank you about that. Okay, so let's continue. Let's delve deeply into what we have for today. All right. In our previous two sessions, now remember that those distributions that we talk about, that's the discrete and the continuous distributions, they were univariate distributions because they dealt with one random variable. Remember, you can either see
Ye-
x,
Yes, just
yeah, you
X
remember,
or
only
use just
x
any
or
random variable. Yeah,
any random variable that is used. Yeah,
but it's
correct.
single.
So yeah, so it was single. So all those distributions were univariate distributions. They are all univariate distributions. Now we in the previous two sessions on discrete distributions and continuous distributions, we explored probability distributions of one random variable, say x. In this section, we will extend many of the definitions and concepts that we use and we have learned in all those other classes. We want to extend them. And in this case, we're extending it in such a way that we have two random variables, say x and y. When we have two random variables, not just one again, we're looking at, in this case, we're trying to get the probability of two random variables and not just one random variable. So let's see more examples. Now, before we delve into it more, to look at the PMF, the PDF, and some functions, the mean, and some other things, let's look at this example so that it will give us, now this example will give us more clearance and more understanding so that the class will not just look abstract, but it will have more meaning as it regards actual science or actual mathematics. Now, joint distribution for discrete random variables. Now remember, we have already given an example of the probability distribution X for the value of a single investment asset. Remember, so when we are talking about, let's say, one variable, for instance, we are looking at a single investment asset. Now, most real investors, because the truth is that most real investors, they own more than one asset. For instance, they own more than one business, right? They can have two investments, maybe they invest here and they also invest here, or even more. But let's imagine they have two investments, and we will look at a simple example of an investor who owns two assets to show how things become more interesting when you have to keep track of more than one random variable. So, assuming this investor has two assets, which are two different random variables. So, how interesting will it be, given that we have always been dealing with one random variable, and now we have an idea, we have a situation that we have to deal with two random variables. In the case of this investor who has two assets. So let's see how interesting it gets. All right, example one. An investor owns two assets. He is interested in the value of his investments in 1 year. So he wants to know the value of his investments because he has two assets. He invested here and he invested here. And he wants to know the value of his investments in 1 year. And we know not every investment have equal uh, yield or equal result. One might yield faster, one might yield slower. One in the long run will have a faster, a bigger yield. One will have a shorter yield, and so on and so forth. So this particular investor is interested in the value of his investments in 1 year. The value of the first asset in 1 year is a random variable X. So the first asset, let's call it the first random variable. And then the value of the second asset in 1 year is a random variable Y. So now we have two random variables. That makes it a bivariate random variable. So we want to see how we can join them together and find their probabilities jointly. Now, it is not enough to know the separate probability distributions because this investor now, he wants to know for both how his total investment will yield in 1 year. So it's not enough for him to just know one and leave the other one. He needs to know the two of them jointly. He wants to know the two of them together. So for him to be able to do that, and for us to be able to help him as actuaries, this requires a joint probability distribution for X and Y. So let's look at this following table that gives us this information. Now, can we see this table? Now, this table is saying that if we look at uh, the first column here, the first column here, we have Y, and under Y we have 0 and we have 10. And here in the first row here we have X, and following X we have 90, we have 100, and we have 110. So X has three uh, values, while Y has two values. So now here we can see that the value here in this second row, this is second row, second column, which is 0.05. This is a probability value that gives us the probability of Y taking the value 0 and X taking the value 90. Let me just give us a refreshment so that we remember. We remember we say the random variable is Y, while the value that the random variable can take is small letter y. And we also said that the random variable for X, the random variable is capital letter X, and the value that the random variable x can take is small letter x. So here, this the values here 0 and 10 gives us the value that the random variable y can take, or it gives us the investment or the value of the investment that the asset y will yield, while the value 90, 100, and 110 here gives us the value of the investment that asset x will yield. All right, so to get the probability, here we see that this probability is for y equals to 0 and for x at 90. The probability here in the third row, second column, 0.27 gives us the probability that x takes the value 100 and y takes the value 0. And finally here, the fourth row, second column, gives us the probability that x takes the value 10 and y takes the value 0. And likewise, this last one, we can interpret it similarly. I believe that is clear. All right, moving on. So this is an explanation to what we gave on top. The possible in the table above, the possible values of x are 90, 100, and 110. So these are the possible values that the investor wants to calculate the probability. What is the probability that the first asset yields 90 in that year, or 100, or 110? Then the possible values of y is what is the what is the probability that the second asset give a yield of 0 or and 10. Now, the probabilities for all possible pairs of individual values of x and y are given in the table. So the table above is the pair of probability. It's not just a probability of one random variable, but the probability of two random variables which have been paired. Now, for example, the probability that s is equal to 90 and y equals 0 is 0.05. Remember? Good. Also, the probability values in this table define a joint probability function. So here now, remember when we're talking about for discrete random variable, we're looking at the p of capital letter X equals small letter x. Remember? But here we're looking at the probability of x, capital letter X equals small letter x, comma capital letter Y equals small letter y. So the table above defines a joint probability function for p of small letter x comma small letter y for the random variables x and y, where p of x comma y is the probability that x takes on the value small letter x and y takes on the value small letter y. So we can represent it mathematically with this quantity here. P of x comma y equals capital letter P of x, giving x equals small x and y equals small y. For example, representing with the values that we have here, for probability here, using this value x equals 90 and y equals 0, we have probability of 90, 0 equal to probability that the random variable x is equal to 90 and the probability that the random variable y equals 0, which gives us 0.05 from the table. Now, the information here is useful to the investor because this investor wants to know, okay, what is he going to get in total when he combines his two assets, his two investments. For example, when x assumes its lowest value, y is more likely to assume its highest value. We will discuss the use of this information further in later sections. All right, so far so good. Is there any question, contribution, area for clarity, and so on and so forth? Hello, are we there? Halima, is there any area for clarity or question? Hello, Mrs. Ebon, is there any area for, okay, Halima says none for now. I can see Mrs. Ebon's hand too. I believe it is clear. So, all right, thank you very much. Let's forge ahead. Now, what is the definition of the joint discrete probability function? Don't forget, we are dealing with the discrete probability function. Now, definition. Let x and y be discrete random variables. The joint probability function for x and y is the function given by p of x comma y, which is probability of x equals small x and y equals small y. Now, this is the definition. So this is the joint definition, the joint discrete probability function. Yeah, so which is clear. I believe it's clear. Remember, for the joint we use summation. Now note that the sum of all the probabilities in the table in example 10.1 is 1.00. This must hold for any joint probability function. So here, remember when we are talking about the PMF, we say that when you sum them, the probability is supposed to give us 1. So because we have two variables, x and y, that is why we have double summation, because we're summing the product of the joint probability of these two random variables for x and for y, and that gives us equal to 1. That must give us equal to 1. That must give us equal to 1. Let us quickly, permit me to quickly take you back to that table so that we can ascertain whether what we have in example 1 is equal to 1. Now here, looking at this table, if we can take our time to sum, do I give us the time to sum these probabilities? 0.05 plus 0.27 plus 0.18 plus 0.15 plus 0.33 plus 0.02. So when we sum these probabilities, 1, 2, 3, 4, 5, 6, we're going to have 1, the value 1. So we can try that later to be able to be sure. All
Is
right,
equal to 1.
is equal to 1, right? All right, thank you very much. Thank you for that. So it's equal to 1. If it is not equal to, if it is more than 1, if it is not equal to 1, then it is not valid. If the sum of all the joint probability is not equal to 1, then it is not valid. We have to prove it. And if we go deeper in probability theory, any probability density function that is not equal to 1, that when you integrate over the interval is not equal to 1. I believe Mrs. Ebu, you understand what I'm talking about.
Yes.
Yes, so when you integrate, that's for the continuous function. When you integrate over the interval, the range, and you do not get 1, then that is not a valid PDF. And same thing with that of the discrete. When you sum all the individual probabilities and you don't get 1, then it is not a valid PDF. So you can do that. We can even in probability theory and distribution, when you have a probability a probability PDF, probability distribution function for any distribution, we can try that. And you try to sum it, or you try to integrate it over the interval and you do not get 1, then that probability is not valid. So in fact, there are about 3 or more axioms of probability. Can we remember? We have the non-negativity, that is the probability cannot be negative. We also have the normality, which is this one that will say that when you sum everything it will equal to 1. And then we also have the what's the third one now? I think I skipped my memory, but I think we have basically about 3 axioms or more, or 3, 4, 5, depending on what you are looking for. All right, so joint probability functions for discrete random variables are often given in tables, but they may also be given by formulas. So usually they are given in tables, but they may also be given by formulas. Now, the PMF now. So let PMF means probability mass function, and we say we use PMF for the discrete case. Let the random variable x comma y be a bivariate discrete random variable with joint PMF f of x comma y. Now, just be watchful. You see that we are using small letter f here. That's to represent the PMF. When you see capital letter F, it represents the cumulative. I'm sure we have talked about this in some previous classes. So therefore, we can define the PMF of a joined random variable as f of x comma y equal to the probability of x equals small x and y equals small y for x comma y in the support of x comma y, and it is zero otherwise. That is, if it's not in support of x comma y, or if it's not in regards to x comma y. If it's not in regards or in support of x comma y. Now here, p of x equals x and p of y comma y equal y small y represents the probability that x takes the value small letter x and y takes the value small letter y simultaneously, and that's why they are joint, because we are considering them simultaneously at the same time. We are considering them all together at the same time. Now, example 2. An analyst is studying the traffic accidents in two adjacent towns. So these two adjacent towns are now our our two random variables, right? Now, the random variable x represents the number of accidents in a day in town A, while the random variable y represents the number of accidents in a day in town B. So the joint probability function for x and y is given by this value. Now, uh, we have p of x comma y equal to e to the power of minus 2 over x factorial y factorial. For x equals to 0, comma 1, comma 2 continually till infinity, and y equals to 0, comma 1, comma 2 continually. Now let's pay attention to the value that we're having here. It looks like a Poisson process. I've not fully wrapped my head around why they are using this exponential function and factorial, but I think I'll get the answer and then I'll talk to us in the next class why we use this this uh, uh, um, this quantity here to represent the joint probability distribution this for discrete. Now the probability that on a given day there will be one accident in town A and two accidents in town B is given by this probability of 1 comma 2. Remember, one accident in town A, this one here represents town A because town A is x, and then two accidents in town B is y. So this gives us e to the power of minus 2 because we have two towns over 1 factorial times 2 factorial. We know 1 factorial is 1 and 2 factorial is 2, right? Then we have e to the power of minus 2. If you can press your calculator. Is able, you want to say something?
Yes, taught by Paulin's formula, we should have e to on the power of negative lambda, lambda raised to the value we're considering.
Mm,
Like I'm looking at it from the angle of the single random variable, and
okay.
then over uh, let's assume that we're using k, for example. So lambda
Mm-hmm.
raised to power k over
Over
k
k factorial,
factorial.
right?
So I can understand the s factorial, y factorial, but I'm looking. I know this is e raised to power minus 2. So is it that 2 is a lambda, and then what about lambda s, lambda y? So I become a bit confused.
Mm.
So
I think what they're actually doing is they are summing the two of them. Let's say minus. If it were only one, it would have minus one. But since it's two, so we have minus e to the power of minus one times e to the power of minus one. You understand?
e to the power of minus 1.
Minus one times e to the power of minus one. E to the power of minus one for the first random variable. Then e to the power of
That's what I'm
minus.
saying. I think lambda by formula is e to the power of because we're not giving any rates here.
Yes,
No,
yes,
you see what I'm saying. So it should be
yes.
e to the power of the average rate timing or something like that, which is a lambda,
Mm,
and then lambda raised to power of all this value of x and y.
Yeah, I think here the lambda is assumed to be 1. So whatever you raise to the power of 1, you still
Aha.
get 1. So
So
I
it's
think I think
assumed, yeah, that's what, so
mm,
it's
I think
assumed
I
to
think
be
that's what is happening there. Yeah, but I'm not too sure, just like I was saying earlier on. But
okay.
I'll dig deeper and see why they are representing it this way.
Okay.
Yeah,
Okay.
so but I think most probably it will be that the value of lambda there is assumed to be 1. Even
Okay.
if you raise lambda to any power of any value, you still
It's
get,
gonna give
if you
you one, yeah.
yeah,
So that's what
if
I'm
you raise 1.
wondering, because if this anyway, since the value is not defined, the lambda rate,
Hmm.
the average rate is not defined, so maybe we're
Yes.
assuming that it's one.
Hmm. And I think probably it may not be an entirely Poisson process, but I'll try and
Mhm.
understand the process that they're actually using. You
Okay.
understand?
All right.
Yes. So, but let's have it at the back of our mind that this is what we get for the joint distribution. All right, forging ahead, and we see the above probability function must satisfy the requirement. Remember that we mentioned earlier on that axiom, that requirement. That's when we sum the joint probability for x and for y is going to give us 1. So if a probability function is given a problem in this text, and usually when we give any problem here, we just assume that it is a valid probability, right? Yeah, but there's a need for us to always test the validity so that we will not violate the one of the most important axioms of of probability. That's when you take the summation of the joint probability, it should give you 1. So for the example above, let's test the validity using this proof, this small proof here, and see whether we'll get it. All right, so let's go ahead. Now here we have we know that we're trying to test that when we take the summation of the joint probability is going to give us 1, right? So we'll come here, we'll take the summation. Remember, our limit is from 0 to infinity. Remember, here, 0 to infinity for x and 0 to infinity for y, right? So we'll come back here and take the sum from 0 to infinity. Here too, we'll take the sum of y from 0 to infinity. And then we'll have our PMF here. Remember, our PMF here, this one, e to the power minus 2 over x factorial, y factorial. So we'll input it here and take the summation and see whether it's going to give us 1. All right, so let's go ahead. Now, here, we can factor out e to the power of minus 2 outside because it's a constant, right? Ms. Sebun, are you there with me?
Yes, yes, I don't want to interrupt. Yes, if I'm
Okay,
confused,
okay,
I will shout out. Yeah.
okay, all right. So we factor out e to the power of minus 2 here because it's a constant. It does not contain, we can take it out because we can take it, and then let this as inverse 1 over, right? If we take e to the power of minus 2 outside, we have 1 over x factorial, y factorial. And then if we separate the two of them, we have the summation from 0 to infinity of x factorial. This summation is for x factorial. And then if we do that, then x factorial here will be constant for y factor for the summation of y ranging from 0 to infinity, right? So 1 all over x factorial will be a constant here for this particular summation. So we can also take 1 all over x factorial outside, which is the same thing because when we say 1 all over x factorial times 1 over y factorial, we will get 1 all over x factorial y factorial. And then our constant here, e to the power minus 2, is outside. Now, from I think Taylor series and expansion, when you take the summation of from 0 to infinity of of 1 all over y factorial, you're going to get an exponential value. Remember? Yeah. So when you take the summation from y ranging from 0 to infinity of this 1 all over y factorial, you are going to have an exponential value. So this gives us this exponential value here. Now, so with this exponential value. This is e to the power of 1. So if we now bring this also a constant, we can now take it back outside again and multiply. We can take it back outside and multiply. So e raised to the power of minus 2 times e to the power of 1. Since the e and e are the same, the powers according to multiplication, law of multiplication, if you are multiplying the same base, then the powers will add. Remember, one of the law of logarithm, indices and logarithm. So here we have e to the power of minus 2 times e to the power of 1, which is e to the power of minus 2 plus 1, which gives us e to the power of minus 1. So that's what we have here. Then we still have summation s ranging from 0 to infinity of this 1 over x factorial. According to Taylor's series expansion, if you expand this, you are going to have an exponential value. So e to the power of minus 1 times e to the power of 1, which will give us e to the power of minus 1 plus 1, which is e to the power of 0, will give us 1. Proof as required. Is that clear, ma?
Yes, like I said, if I'm confused, I will kind of call your attention. It's well explainable.
Okay, all right. Thank you very much. Okay, so now let's look at marginal distribution for discrete random variable. Now, I want us, like I said earlier, when we say marginal, I want us to think of it as in a joint probability distribution, we are trying to calculate the probability of one of the variable. They are already together, but we're trying to calculate the probability of one of them and separate it separately. That is what we call marginal distributions for marginal distributions. So we also have it for the discrete case and also for the continuous case. Now, for the marginal distribution for the discrete random variables, once we know the joint distribution of x and y, we can find the probabilities for individual values of x and y. So once we know their joint distribution, we can find the probabilities for their values separately, for the two random variables separately. Now this is illustrated in the next example. So in this example, which is our example 3, the table, remember this is our table from example 1. The table of joint probabilities for the asset values in example 10.1 or example 1 gives us the following. Remember the table? I will not go over to explain the table again. Now, here we can see that P of x equal to 90 is equal to P of x equal to 90, comma y equal to 0 plus P of s equal to 90, comma y equal to 10. Do we understand? Which is equal to 0.05 plus 0.15. Let me explain more. Here, P of x equals to 90 gives us for 0 and it gives us for 10 when y equals to 0 and when y equals to 10, right? So when we sum these two, 0.05, the probability is 0.05 plus 0.15, we're going to have 0.20. 5 plus 5, 10, 2 0 carry 1, 1 plus 1, 2, so we have 0.20. So the probability for s equals 90 from the joint probability distribution gives us 0.20. Likewise, we can do that for y equals 0. For y equals 0, we have 0.05 plus 0.27 plus 0.18, which gives us 0.50. Yeah, and then for y equals 10, this gives us 0.15 plus 0.33 plus 0.02, which gives us 0.502. Alright, so here we have for y taking the value 0, we sum 0.05 plus 0.27 plus 0.18, which gives us 0.50. So basically here we can say if the investor wants to know the probability that when that his second investment will give the value 0, will not yield anything, then with a 50%. chance here. So he will know the decision he needs to take, and so on and so forth. Now, if he also wants to know the probability that the second asset will yield 10, it can be found in the same way. When we add 0.15 plus 0.33 plus 0.02 plus 0.50, which gives us plus 0.2, which gives us 0.50. So he has equal chances of his second investment, which is Y, yielding 0 and also yielding 10. Whereas for his first investment yielding 90, he has a 0.20% chance, and for his investment yielding 100, he has a larger chance, which is 0.60, and 110, he has 0.20. All right, so the individual distributions for the random variables x and y are called marginal distributions. Marginal distributions. All right, so definition of marginal distribution. The marginal probability functions of x and y are defined by the following. So for x, we have p of the random variable x is x, p of x equal to the sum that of y, while p of y even of y will sum that of x. So this is how we obtain the marginal probability distribution. In fact, from this formula, we can see how easily what we did here. For y, we are summing for the x 90, 100, 110. For x, we are summing for the y 0.5 and 0.1, right? All right. So the joint probability function for numbers of accidents in two terms in example 10.2, remember, was p of x comma y equals e to the power of minus 2 over x factorial y factorial. Remember, that's what we got. Now, so let's see how we can use, we can modify this formula to give us the marginal probability of x and the marginal probability of y. Now, to do that, we have this quantity here. We have p of x, where x is equal to. So now we are considering only for y. Remember, we're summing all the individual probabilities on that y. So this gives us. So here we're only taking the summation for y, while negating the summation for x. So this gives us summation for y from 0 to infinity e to the power of minus 2 over x factorial times y factorial. So this is equal to here. You can see since we are looking at y from 0 to infinity, e to the power of minus 2 over x factorial is our constant. So we'll factor it out. And then we have summation y from 0 to infinity 1 over y factorial. And based on Taylor's series expansion, this is equal to e. So here we have e to the power of minus 2 over x factorial times e. And when we do that, when we multiply, e to the power of minus 2 times e to the power of 1 gives us e to the power of minus 1 over x factorial. Likewise, when we do the same thing for the marginal probability for y, we get e to the power of minus 1 over y factorial. Now, each marginal distribution is Poisson with lambda equals 1. Okay? Yeah, Mrs. Ebun, this has answered our question now.
Yes, yes.
Yeah, so each marginal distribution is a Poisson process, and
It's
it's assumed that
lambda
lambda
equal to
is
1.
equals 1. Yeah, so in fact, it explains what we are talking about earlier on. If it is
Yeah,
1, then it makes sense.
yeah.
Yeah, so this is the basic assumption uh, for the marginal distribution. All right, so how do we use the marginal distribution? We want to look at the actuarial from the actuarial point of view, and we'll see some examples so that to make more sense to what we are doing in actuarial maths. Now, once the using the marginal distributions, once the marginal distributions are known, we can use them to analyze the random variables x and y separately if that is desired. Yes, so like I mentioned earlier on that if we already have the joint the joint distribution, we can use it to determine the separate random variables, to analyze the separate random variables. Example, the next example, example 4, for the asset value, remember the asset value joint distribution in examples that we use in example 1 and example 3, we see that the probability of x greater than or equal to 100 is equal to 0.60 plus 0.20. Let me go back so that we'll see it clearly. Now here, for this value, we have here we have 0.20 plus 0.60 for x greater than or equal to 0. Remember, our formula for probability was greater than or equal to. So we're going to sum, we'll do 1 minus probability of less than. Remember, all the less than or equal to, since it is equal to. So we have 1, so we have 0.20 plus 0.60 or 1 minus 0.20. So this gives us 0.80. And then for probability of y greater than 0, strictly greater than 0. Let's go back to the table so that to be clear. Strictly greater than 0. So we are considering everything that is more than 0. So everything here. So 0.15 plus 0.33 plus 0.02, which gives us 0.50. I believe that is clear and straight to the point. Now the next example, for the accident number joint distribution in examples 10.2 and 10.4, both x and y were Poisson with lambda equal to 1. Thus, probability of x equals to is equal to probability of y equals to, which is equal to e to the power minus 1 over 2. We can evaluate this and get the answer. Now, using the marginal distributions mean and variance, the mean and variance. Remember mean expectation and then the variance, which is the sums of deviation. Now, in the following examples, we will calculate the mean and variance of the random variables in the last two examples. This information is important for future reference since we will find these expectations by another method involving conditional distributions in our next section. Now, example, mean and variance. Example of marginal distribution when we're trying to obtain the mean and the variance. For the asset value joint distribution in example 1 and 3 above, the expectation, remember expectation, which is the sum of the probability times the random variable. Remember the formula for expectation? We're going to do it more when we start calculating premium, and so I believe maybe they must have started teaching that in the other in the some of our other classes. Yeah, but I think if you are looking for expectation, you are multiplying the probability times the value that the random variable can take. So so this is just 90 times 0.2 plus 100 times 0.60 plus 110 times 0.20, which will give us 100. And the same thing when we look at the mean of y gives us 0 times 0.50 plus 10 times 50. This is 0 and this is 5. 10, it's like 10 multiplied by half, it gives us 5. Now, to find the variances, we first calculate the second moment. The second moment, we know that variance is equal to the deviation. There's a general formula for variance, which is summation y squared minus summation y all squared, or summation s squared minus summation x all squared. That will give us variance. There's an expansion for that formula, maybe if you can remember. So to get the variance, we already
So,
obtained.
sorry, if I may
Yes,
quickly ask a question here.
yes,
I
yes.
thought we were going to use the formula for mean and for the mean and variance for Pausen, which means just the lambda. So is it because it's joint? You know the formula for the first moment is expectation of s equal to lambda.
Yes.
Aha. So why are we going through this? It's like saying S probability of, I mean, probability that S takes the value of 90 plus 100 probability of X takes the value of 100. So why are we using that? I just want to know. It's not that I'm confused with the figures.
Yeah,
But
good
I
question.
think it being a thousand, we should just go for the lambda straight.
Okay. Now, we can have a situation whereby it may not necessarily be Poisson. You understand? You know, this is joint probability. So, that is why we just there's a general formula for the mean, and then there's a general formula for variance. Expectation of x. I don't know. Did we solve that in this class? I don't think so.
No,
But
no, I don't think
yeah,
so. Yeah.
yeah. But there's a general formula, I think, for expectations.
Okay.
Expectation of random variable. There's a topic that was supposed to do
Yeah, yeah,
expectation.
yeah, we did.
We did,
But
right?
what I'm saying here, yeah, we
Mm,
did. But what I'm saying here is because it's thousand, that's why I'm saying that. I know that this is how to solve the problem. I was thinking if I have to do it by myself, I would
mm.
think because it's thousand, I would just go for the formula saying A of S equal to lambda as the general Poisson distribution. That's why I'm saying this.
Okay. Let's see. Let's see. Can you? Well, I'm not sure it will give us the answer if we use that.
Yeah,
Um,
I'm
it won't
just
give us what we're
wondering
looking for.
why. Yeah,
It won't give
because
us what we're looking for.
the what's it called? The distribution takes powers. Then that's why I'm saying all this.
Yeah, I understand. I
Yeah,
understand.
yeah.
Yes. So, going forward, so when we use the formula for the mean, we multiply, that's E of x. We have gotten the mean already. But to get the variance, remember I said that the variance is, if you expand the formula for the variance, you get expectation of x squared, expectation of x all squared minus expectation of x squared. I don't know whether you understand what I'm saying. Expectation of x all squared. So we're squaring both the expectation and that value.
Yes, I understand this. I only
Uh,
asked that question because we mentioned Poisson distribution. I
okay,
understand all
okay.
this calculation. Yes, I did.
Okay, okay. All right, all right, all right. Oh, thank you very much. So
Yeah.
if we do that, so we're going to get these values for this value for the mean of x and mean of y, and then this value for the variance of x and variance of y. Now looking at this variance of x and variance of y, can we make any inference? Can you make any inference concerning it in relation to the asset that the man we are talking about, the asset of the man? Can you make any inference as a practical inference? Okay. All right. So let's further it. Let's further it then. All right. So finally, for the mean and the variance, for the accident number joint in example 10 and 10.2 and 10.4, both x and y were Poisson with lambda equals 1. Thus, okay, okay. See, they are using the formula you are talking about, Mrs. Seven. Hello.
Oh, okay. I didn't mute. Yeah, yeah.
Yeah, so you see, they use that formula. They say, for example, for the accident number, that
You
accident
see what
number.
I was saying? Yeah.
Yes, yes,
So
yes.
that was what I
Yeah,
was expecting.
yeah. So it
Yeah.
follows. For this one now is for the asset value example.
Oh, yeah, for the
Mhm.
first one. Yeah, you see, that was why I was confused. Yes, I
Yeah,
got it now. Yeah.
while
So
this
the
is for the
this
accident.
example was a ha. So
Mhm.
I mix it up thinking that we're treating this example. You see what I was asking? Because I was
Yeah,
thinking being a thousand, it should take this method rather than,
exactly.
yeah, the first one was asset. Yeah, I got it now.
Yeah, it's clear now. It's clear.
Yeah,
It's clear
yeah.
to me too. Now.
Clear to you too. That's good.
Yes, 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 yes. I think it was an oversight. I actually saw it while preparing, but yes. So let's
Okay,
further it.
that's good. So I'm clear now.
Yeah, all right,
Yeah.
that's nice. Okay, so we have so far so good. We have talked about the joint distribution for the discrete random variable, and we have seen many things concerning that. We have seen the definition of the PMF. We see since it's discrete, it's PMF, right? And then we have seen some examples. We have seen how it works. We have seen it gives us some sense, and we understood. In fact, it's even making more meaning. Even though we are seeing how interesting it is, we are digressing from the normal univariate random variable. But here, we are seeing more explanation and more understanding. So we have seen that for the joint discrete. So now let's look at for the continuous case, for the continuous joint distribution for the continuous random variable. Now, before we do that, let's take a brief recap of the continuous distribution for the random case. Now, remember, when we're talking about the probabilities for a continuous random variable x, that's one single random variable, we say that they are found using a probability density function. Remember, PDF, f of x, f of small 1x, because it's single, with the following properties. We say it is non-negative. That is, the f of x for all greater than is greater than or equal to 0 for all values of x. So the probability can never be negative. Also, we see the total area bounded by the graph of y, f of x, and the x-axis is equal to 1. So when you integrate over the intervals, it's going to give you 1. That's for the continuous case. For the discrete case, we say when you sum over the interval, you get 1. For the continuous case, when you integrate over the interval, you get 1. Now, the third axiom, we say, or the third condition, or the third property, we say when you are looking for the probability in an interval, in an interval given is given by the area under y. So the value is given by the area under y between x equal to a and x equal to b. So this gives us p of a less than or equal to random variable x less than or equal to b is equal to integral b to a, because these are the what intervals b to a. B is a greater interval, y is a small lesser interval. Or b is a is the interval before the next interval b. So we have b to a, just like we represent in integration, f of x dx. Now, I believe we have remembered this property. Now, it is important to review these properties since we are talking about the joint probability density function, because we are going to define it in a similar manner. So we are going to do that now. We'll review this property. We'll review using these properties for the single case. We'll review it and use the double case or the joint case or the bivariate case to have a clear uh, PDF. The joint probability density function for two continuous random variables. Probabilities for a pair of continuous random variables x and y must be found using a continuous three-valued function of two variables. The function of two variables will define a surface in three dimensions. Probabilities will be calculated as volumes under this surface, and double integrals will be used in this calculation, just like we use double summation for the two uh, discrete random variables. We will use double integral for the two continuous random variables jointly. So, in reviewing the properties, we have first of all that f of x comma y, now we are using 2, x comma y, must always be greater than or equal to 0 for all x comma y, which means that's the non-negativity axiom. We're saying that it must not be negative. Then secondly, the total volume bounded by the graph of z, now z we are considering the two of them, is f of x comma y, and the x to y plane is 1.0, it must give us 1.0. So when we integrate both of them, that's integral from negative infinity to infinity. Uh, that's for the x. The first integral is for the first random variable or the first value here, x, while the second integral is for the second value here, y. So for each of the case, we have the x, the y. So uh, when we integrate the joint continuous distribution, we're going to get 1. So now we're modifying the conditions for the single case here, as we have here, the non-negativity, the integral, and then the for the intervals. So modifying it to fit in the properties for the double case, the bivariate case. Now, whereas for the last property, when we have the two random variables bounded by these intervals, a a and b, that's for the x, then c and d for the y. Now, it's going to is given by the volume between the surface z is equal to f of x comma y, and the region in the x to y plane bounded by x. X will now have x equals a and x equals b because x is a immediate interval, while y will have y equals c and while y can be d. So these are the two bound. It's a continuous case, so we are looking at the result that falls within this boundary. So in S case, the result that falls between the boundary A and B, and that's why it's continuous. For the discrete, it's just a single value, but because we are looking at the continuous case, so it can be it's a continuous, so we don't know where we can't determine the particular value, we can only determine it using an interval. So in doing that, we have this integral defined by uh, the defined by the boundaries b to a, that's for the x, for the random variable x, and then d to c for the random variable y, so, and dy dx as as it should be. All right, so let's look at example uh, 7. Even though we are seeing example 10 here, but it's our example 7 for this class. Now, remember our example 10.2, that's our example 2, when we're talking about an analyst who was studying traffic accidents in two adjacent towns, town A and town B. Remember? Now that example gives us a joint distribution for both towns, the number of accidents that happen in both towns. Now let me just give a small example. Remember, if we're looking at the number of the number of accidents that will happen between the two towns jointly, then that's discrete because we're looking at a particular value. But say for instance, we're looking at the time for the occurrence of this accident. You see now it is no longer a discrete case, it's now a continuous case. So using that example, if we are to modify it to be a discrete case, a continuous case, then we will change the variable. We will no longer look at the frequency of the accidents, but we will now look at the time at which it will occur, which will now make it a continuous case. So that example will give the joint distribution of x and y, the discrete random variables for the number of accidents in the two towns. Now, in these examples, we look at the continuous random variables S and T, that is the time between the accidents in towns A and B respectively. So the time gives us the continuous case, while the number of accidents between the two towns gives us the discrete case. So the time between accidents in town A and B respectively, the joint density function of S and T, uh, X and Y gives us for the discrete, S and T gives us for the continuous. So the joint density function will give us this value f of s comma t, which is called e to the power of minus s plus t. Now you remember when we were doing that one, for that case we have e to the power of minus 1 times e to the power of minus 1. That's for the two case. Can you remember, Mrs. Sebu? So e to the
Yes,
power
yes.
we had e to the power of minus 2, right?
Yeah.
So
But
for this
now
case now,
it's over an interval.
so it's over, and so now it is we can't they are not discrete, so
Yeah,
we're multiplying e to the power of minus s times e to the power of minus t for the
yeah,
two of them,
yeah.
which gives us e to the power of negative open bracket
Because
s.
the time is the interval is defined over a particular period, not just one period.
Exactly. So we have the PDF as this e to the power of minus s plus t, and then s is greater than or equal to 0 because no event can happen in no time. Every event must happen in a particular time. So that is why s is greater than or equal to 0 and t is greater than or equal to 0. So we will first check that the total volume under the surface is 1. So let's check, just like we did for that other one, remember? So we have our double integral 0 to infinity. This is our limit, s greater than or equal to 0 continuously. So with 0 to infinity, Then same thing for t, the second for the second term, the time in the second term, same thing. So we have our double integral e to the power of minus open bracket s plus t ds dt because we have the double integral. So this gives us by simple integration. When we do that, we integrate the first one over the interval s infinity to 0, infinity minus 0, we will get 1. And then when we do the second integral, we will get this, we will get all of them gives us 1. Right? It's clear, right? Or you need more explanation?
Yes, it's clear.
Right. So this shows that it's valid. It has satisfied the second condition, that the probability given satisfied the second condition. Now the density function can now be used to calculate the probability. So now let's calculate the probabilities. For example, the probability that x is less than or equal to 1 and t is less than or equal to 2 is given by the following. Alright. So now we want to calculate jointly the probability that s is lies between 0 and 1 and t lies between 0 and 2. So here we're integrating over the interval. For the first one, for the t, this is for we have 2 and 0, and then we have 1 and 0. That's for the two. For s we have 1 0, and then for t we have 2 and 0, 0 and 2 to 0, integral from 2 to 0. So and then we have our PMF here, PDF here, the SDT. So when we integrate, put in our interval, we will get this value 0.547. Do I need to explain more?
No, it's clear.
All right, all right. So this gives us the joint probability for the continuous case. All right, so the marginal distribution for the continuous random variable. Remember what we said in the marginal distribution for the discrete case? So we'll use the same method to get the marginal distribution for the continuous random variable. By marginal, we mean that we already have the joint probability, and from there, we want to calculate for the individual. And remember the formula that we gave for the discrete case. So yeah, let's go ahead and do that for the continuous case. Now for continuous functions, the addition is performed continuously by integration, while for the discrete case, we perform continuously by summation. Thus, the marginal distributions for a continuous joint distribution are defined by integrating over x or y instead of summing over x or y as in the discrete case. Now definition, let f of x, y be the joint density function for the continuous random variables x and y. Then the marginal density function for x and y are defined by the following. So for x, we have integral negative infinity to negative infinity of x, y dy. Remember how we did that? When we have x here, we have dy here. When we have y here, we have dx here. Now, the probability distribution of x and y are referred to as the marginal distributions of x and y. So let's look at some few examples, and then the solution, and then we'll call it quits for today. Now, example 8. For the sick leaf random variables of example 10.9, okay, we didn't talk about the sick leaf. There's supposed to be an example here. But I didn't mention. We didn't mention that example. Okay. In that case, should we skip to the next example since we didn't mention? Or let us look at it. Let's just look at it since we have an idea. Remember, I'm using the textbook probability theory and distributions for actuarial sciences. The textbook is in. I've posted the textbook in the drive. So if you want to check, go ahead and check. You can go ahead and check to get the complete example for the least example 10.11. I believe that's clear.
Okay, I'll try and check the textbook.
Okay, there's a
Is the
test.
material you give to us on the drive, is it?
Yes, it's in the drive.
Okay.
I've sent it a long time ago. Yeah.
I knew that's why I said the material you give to us in the drive.
Yes, ma'am. Yes, ma'am.
Okay.
That's it. So when you consult it, you have more information on this.
Okay.
And probably you will see the example for the sick leave too. That's the beginning, the question. When they're talking about the sick leave,
Okay.
you will see that too. Yeah.
All
So
right.
let's watch ahead. So using that example, we see that the the PDF is equal to 2 minus 1.2x minus 0.8y. That's the PDF for that example. So for this interval, for x lies between 0 and 1 and y lies between 0 and 1, the marginal density functions are, so let's do the calculation now. Remember the formula? We integrate over the interval of, now here we're looking for x, we integrate over the interval of y, and for y, we integrate over the interval of x, right? Just like we explained here. See it here? All right. So here we are. So for x, the marginal distribution for x represented as f of random variable x of x is equal to integral 1 to 0. Now, 1 to 0 here is for y, right? The limits or the range of values for y. We use it here. So we integrate this function 2 minus 1.2 x minus 0.8y dy with respect to y. So we have here for integrating with respect to y, here from simple integration, this gives us 2 y raised to the power of 1 over 1 minus 1.2 x y raised to the power of 1 over 1. Remember, minus 8 y raised to the power of 1 plus 1 over 1 plus 1. That's 8 raised to the power of y squared over 2. Right? Remember? So 2 cancels 2
No,
here,
that's
1.
still the equation. Don't worry, it's clear to me.
Okay, it's clear, right?
Yeah, it's very clear. Yeah.
Yeah, I'm trying to give more explanation for
Okay.
those who will be
Okay.
offline, and then
All
yeah,
right.
yes, that's why
Okay.
I'm asking so that when you agree, I know that I'm on the right track.
Yes. 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 I agreed.
So 2 will now based on by simple integration, 2 will
Yeah.
divide 8 divided by 2,
8.
which
Yeah.
gives us 4. Mhm. So when we introduce our range 1 to 0, we will
That
introduce
means
it for 1
substituting the
first.
value. Yeah.
Yes, then minus that of 0. So when we
Mm-hmm.
do for that of 0, this gives us 0, 1.
0.
This gives us 1,
No.
right? This
You
was
say
for
if you
2.
substitute for 0, if y is
Okay,
equal to 0,
okay for 1. Let's start for 1. When we start
1,
for
yeah,
1,
this will give us
is
2
2
minus
minus
1.2x
x
minus
minus
4.
minus 4. Good.
Here.
So then y for 0, it gives us uh
Everything will be 0, if I'm right.
no, is it 0? Okay, yeah, this is 0, this is 0, 0. Everything will be 0
Yes.
exactly.
Yeah.
Exactly. So we have our 1.6 minus 1.2x.
Yes.
Then for y, the same thing. We follow the same methods
Yeah.
using the range of values of x, and then we have this particular value as our marginal uh, probability distribution for the continuous case. Now, also, when we do the same thing for this example, I will allow us to go and check this example. Maybe we'll come and explain more in the next class. I believe it's straightforward. So for a joint distribution of waiting times for accidents in the example 10.10 that we talk about, we say this is the PDF, and we say the range is 0 to infinity. Here also the range for t is also 0. The range for s is 0 to infinity, and the range for t here is 0 to infinity. And we're looking for the marginal density functions. So for f of s given f s of s, right? Fs of s, we have integral of this function. That's for the marginal
Mm.
distribution. And then our range here is 0 to infinity e to the power of minus s of s plus t dt. So here, if we expand this, we have e to the power of minus s times e to the power of minus t. And we factor out, since we're integrating the range of the t, since we are integrating on the range of the t, then e to the power of minus s is a constant, so we cannot factor it out and integrate over the interval of the t, because here we have t here, e to the power of minus t. So when we integrate, we have minus, when we integrate e to the power of minus uh, t dt, this gives us e to the power of minus s. Likewise, when we do the same thing for this, we get e to the power of minus t. All right, finally, this example. Then for the Poisson case, that waiting time in example, that when we say that the marginal distribution of S and T each have an exponential distribution with lambda equals to 1. Remember, since we say that the lambda is equal to 1 for the Poisson case, now that it is, sorry, now that it is continuous, it becomes exponential. It's discrete, that's why it was Poisson. Now it's continuous, so it becomes exponential. The lambda there becomes exponential. So thus, expectation of S is equal to expectation of T, which is equal to 1. And then probability of S greater than 1 is equal to probability of T greater than 1, which is e to the power of minus 1, as calculated. All right, so exercise. These are our exercise for next class. I know you're going to say we have no rested from the exams by giving exercise, right?
Really, it's good so that we can try our understanding of the topic. It's
All
just
right.
time. Yeah.
Yeah. So this exercise is just one. It will give us an opportunity to brainstorm to see how we can understand more of the topic. In fact, I would recommend that as we go through the textbook, let's go down and see more of the exercises and see how we can uh, attempt them. By doing that, by doing such, it gives us more idea and more understanding and drives us deeper into the course so that we'll be masters of the course and have more experience. So here, let me quickly read through the exercise. It says a company has 5 CPAs, 3 actuaries, and 2 economists. Two of these 10 professionals are selected at random. So here, if you add all of them, you have 10. 5 plus 3 plus 2, 10. So two of these professionals are selected at random to prepare a report. Let X be the random variable for the number of CPAs chosen, and let Y be the random variable for the number of actuaries chosen. We're considering 2 bivariate. Remember? Construct a table of the joint probabilities for X and Y and the marginal probabilities of X and Y. So we'll see that in the next class. We'll see that in the next class. I also indulge us to consult the textbook and consult other materials to see how we can get the result to uh, this exercise. All right. So recap. Conclusion. In conclusion, we gave a brief recap of our last class. We did introduction. We explained that in our last class we talked about the univariate probability distribution, both the discrete case and the continuous case. And today we want to talk. We say, okay, what if we are trying to see a case whereby there are two random variables? How can we determine their probability? So that's why we say that's where the bivariate or the joint distributions come into play. And we looked at an example for the discrete case and also an example for the continuous case. When we do that, we give a definition of the joint discrete probability function. We explain what a marginal distribution for the discrete case means. We say the marginal means we're trying to calculate the individual probability from the joint probability, given the joint probability. I would say for you to do that, you must already have the value for the joint probability. Then you can now also calculate the marginal distribution. So we also look at how we can use the marginal distributions for the discrete case, how we can use the marginal distribution for the continuous case. We also look at the joint distributions for the continuous case and also for the continuous random variable and the marginal distribution for the continuous random variable. All right. So thank you for being in the class up until now. If there's any questions, comments, challenge, addition, contribution, or clarification, please, you can go ahead.
The only thing I've noticed is that the attendance form is not being sent out.
Oh, okay. Yeah, Alima is supposed to do that. I think she has logged out.
Yeah, either
But
Halima or Usman, one of them supposed to be here and send in the attendance. Sorry, good evening. I'm just joining.
okay, you're welcome. That's you.
Yeah, thank you. Evan, good evening.
Good evening. How are you?
Yeah, I'm good. Actually, I have another class, so I just concluded the class and I just decided to log in and say hi.
Okay. So thank you for
How was the
being.
exam, by the way? The midterm exam.
It was okay for me, I would say, but
Yeah,
the time factor is the only problem. Like I
yeah,
was telling Jacob, I did the whole exam in one day. Because that
yeah.
weekend I was not available at all.
It's
So
all
but
right.
it
We
was
hope we hope that when we are doing the other exams or tests, you will have time. Yeah, so
Okay.
that
Let's hope
you will
so.
do justice to it.
Yeah, hopefully,
Yeah.
yeah. Sure.
And I hope we'll be giving correction. I mean, marking and correction. That's another
Of
thing.
course, of course.
Yes, of course, for sure. That will be done. I think
So,
probably by next week,
okay.
we should get that.
So, in all fairness, there's no question from my own hand here.
Yeah.
For
All right.
I know
Well done, Jacob.
people are occupied, but if we can encourage us, the student, to participate, that will make the class more lively.
Exactly.
Exactly, exactly.
So
So, all
that's
right,
it.
we'll put that into consideration.
Yeah,
We'll see how we can get to those all the students and then talk to them
yeah.
to
It's
participate.
well done, and thank you very much.
All right. Thank
Okay.
you for listening. Thank you for being
Oh,
here. We
Yeah, I
hope to
just
meet
called
again in our next
Usman
class.
to actually send the attendance. I don't know if he can be here in a minute so that you can fill in the attendance.
okay. You want me
Is
to
there
wait?
is there it? We already know she's
Yeah, of course, of course. I mean,
yes, yes.
there's no need for that.
Yeah, so no use. So let me
Yeah,
just
sure.
All
take
right. Have a good
this.
night ahead.
And you too,
We'll
everyone.
meet in the
Bye
next
for
class.
now. Thank you
Bye
very
for now.
So,
much. All right.
bye.
Bye.
Good
Bye.
night. Good night.